So hi everyone, my name is Pradyumna Rao. I'm from S14. My roll number is 251PS026. And today I'm here to explain 5 proofs on infinite sequences. So we'll be looking at the proofs one by one. The first we are given that we have two sequences, two convergent sequences, xn and yn, which converge to x and y respectively. So the first proof that we are going to tackle is that if xn plus y is a combined sequence, then we have to prove that the combined sequence, the new sequence, will convert into x plus y. So how will we do that? We will be looking at the further slides. So in this theorem, we have to prove that xn plus y converges to x plus y. So we have been given that there are two sequences xn and yn, which will be converging to x and y respectively. So let us take a positive epsilon such that there exists a k in natural number such that the modulus of xn minus x be less than epsilon by 2, such that n is a positive number greater than k1. And also let's take k2 let's take k2 which belongs to natural number such that yn minus y be less than epsilon by 2. This is the epsilon k method which we will be using to prove this theorem. And let us define k to be equal to maximum of k1 and k2. Then for a small case n greater than k, let's take in the LHS, let's take xn plus yn minus of x plus y, the modulus of xn plus y minus of x plus y. We can expand this as we can open the brackets and write this as xn minus x and plus of y minus y. And by the triangular inequality, we can open this and we can show that this is the LHS is less than equal to xn minus x plus modulus of y minus y. And as we know that the modulus of xn minus x is less than epsilon by 2, we can write that this thing is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. And since epsilon is an arbitrary positive number, we infer that xn plus yn converges to x plus y. One proof done. Here are a few examples. Here is one example in which cos n by n converges to 0 and n minus 1 by n converges to 1. And so we know that cos n plus n minus 1 by n converges to 1. And we can solve this by the same method. We can check and prove this by the same method if we use. Okay. So there was an inconvenience with the projector, so I had to use the blackboard again. So we'll be doing the second proof over here, in which we will be proving the second theorem that we have here. We have to prove that xn y converges to xy. So what we will do for this is, first let us take an equation. Let the equation be xn y minus of xy. We can add and multiply few terms in this. Add and subtract few terms in this, and it should be equal to xn y minus of. Let's subtract xn and y from this, and because we subtracted, we should also add the same term again. Xn and y minus of xy. Now applying triangular equivalence for these two terms and these two terms, we can write that this is less than equal to xn y minus of xn y plus of xn y minus of xy. As you can see, we can take xn common from this term and y common from this term. So this will be equal to xn and yn minus y plus xn minus x into mod of y. So after this, as we know, xn and y are two convergent sequences. So all the convergent sequences are bound by an upper limit. So let us assume m1 let M1 be upper bound of xn. Let M1 be upper bound of xn. So what we can write is modulus of xn is less than or equal to M1 for all n. So now that we have modulus of xn less than or equal to M1, we can put this in this equation, and we can further on write the same equation as because it is an inequality which is lesser than or equal to M1. So inequality again comes over here. So we'll be writing that the LHS which is written over here will be less than or equal to M1 into M1 into y minus y plus of y modulus of y into xn minus x. Now let us define a new constant, that is n. Let n be such that m is equals to max of m1 and modulus of y. Let m is equals to max of m1 and modulus of y. So because of that, we can put this m in this equation. We can substitute m1. We can substitute this m1 and y as m, which is maximum of m1 and modulus of y, which will be always because this is already an inequality. The inequality doesn't change. So the inequality will be LHS, which is as it is, and LHS will be less than or equal to m into y minus y plus of m into plus of m into xn minus x. So after this, we'll be using epsilon k definition. Let's say epsilon k definition. It's sometimes called as epsilon n definition. It doesn't matter. Let's take it as epsilon k. I won't write the entire definition over here. I'll be writing that for any epsilon, for any positive epsilon, we can write that there exists a k1 such that xn minus x is less than, and according to the original definition it should have been epsilon, but as we know that epsilon is an arbitrary constant, we can write it as epsilon by 2, which won't affect our inequality, which is less than equal to. And using the same definition for y as well, I am writing for any positive epsilon there exists a k1 such that y minus y, the modulus of y minus y will be less than equals to epsilon upon 2. Now this is our main equation. Let me mark this as star equation. We'll be substituting these two. This is our main equation, and by substituting this equation and this equation in the main equation, what will be getting is we'll be having this is as it is, like this. Again, less than equal to m into, by substituting y minus y by epsilon by 2 over here, we'll be having epsilon by 2 plus of m again, and this time xn minus x is again less than epsilon by 2. So simplifying this further, we'll be having m gets cancelled and m gets cancelled. So we'll be having epsilon by 2 plus epsilon by 2, which is less than equal to epsilon. Now let me know that epsilon is an arbitrary constant, an arbitrary positive constant. So we can assume that epsilon as epsilon tends to 0, we can write that x and y tends to x1. So with this we have proved our second theorem. Example, let xn equals to, let my first sequence xn be n plus 1 upon 2, and my second equation y, my second sequence y, let's just be equal to 1 upon 1 minus 1. Now we know that the xn converges to 1 by 2 and y converges to 1. So using this property, what we get is xn and y should be converging to x and y. That is 1 by 2 is 1, which is equals to 1 by 2. So we have verified that the proof that the theorem we just proved is right. So let's move on to our next proof. We have to prove that Cxn converges to Cx, where C is a constant in this, and we can use the proof which we just used earlier, in which we just proved that xn minus converges to xy. What we do here in this is we'll just take y as a constant sequence, y equals to c. We just take the constant y equal to c. Y is a constant c. This is a constant c. And when we put this particular equation in this equation, if we substitute, then what will we get is x into c will approach to x into c, which is again what we had to do, that c into xn, the sequence c into xn converges to c into x. So this is a proof, and yeah, that's all. Okay, now let's move on to our fourth proof. Okay, so our fourth proof is that we have to prove that xn minus y converges to x minus y. So for this fourth proof, we'll be using our both the proofs which we used in the first two proofs, in the first two theorems. So we'll be using our first theorem and second theorem as well. First, let us use our second theorem by theorem 2. So what we did in theorem 2 was, let us do the theorem 2 states that Cxn converges to Cx, saying that C is a constant and xn tends to x. So what we will be doing is, let's replace C as minus 1 and xn as y in this equation. When we substitute, we'll be getting the minus of y, the new sequence minus of y tends to minus y. This is an important thing, so let me just take a standard and mark it as equation 1. And now I'll be using equation 2 for this. My theorem 2 states that if there is a sequence called xn plus y, if there is a sequence called xn plus y, which xn is a converging sequence, y is a converging sequence, and both converge to x and y respectively. So the new sequence xn plus y will be converging to x plus y. Let me call this the second equation. Now let xn be xn and let me goes where this thing will be converging. This thing will be converging to the sequence. Will be converting to the so the new sequence that will be getting is xn plus y, and this will be converting to x plus minus of y. How did we get this minus y? We got this minus y using this one in this, using equation 1 in this equation, and we get minus y. So this is basically x minus y, and that is what we had to prove, and hence we proved the equation. Okay, let's come to our final proof of the day, and in which we have to prove that there is this theorem called xn by 1, which states that xn by 1 converges to x by 1, provided the sequence y is not equal to 0 and y is not equal to 0. So to prove this, first we have to prove that the sequence 1 upon y will be converging to 1 by y. So we'll be doing that by epsilon k definition. First, to prove, so we have to prove that 1 by y equal to 1 by y. So let's again use the epsilon k method, epsilon k definition. Let's define alpha, which will be equal. Let's define alpha as y by 2, saying that alpha is a constant. Such that so y minus y is less than alpha. If we can further, we can just multiply this by minus sign and change the inequalities, such that minus y by 5 is greater than minus alpha. Equation 1. And now, so after this, I can write y as y minus 1 and plus of y, and y triangle inequality. I can write the same equation by clubbing these two terms. I can write the triangle inequality as y minus 5 plus of y. Solving further, what I'll be doing is I'll be taking this term to the LHS and this term towards the RHS. So minus of y minus y will be less than equal to y minus y, and let me call this equation as equation. Now from 1 and 2, we can substitute the equation 1 in equation 2. We can put the value of minus of y, values of y minus y as minus alpha. So this is going to be minus alpha. Minus alpha is less than equal to y minus of y. And here alpha was minus of alpha.
सही है
Here my alpha was minus y by 2, which is less than equal to y minus mod of y. So what are the derivatives is, which then simplifies to mod of y by 2 is less than equals to 2 by mod of y. Now let us consider an equation. Let's say 1 by y minus 1 by y. This can be further simplified as y minus y upon y into y. Now by using equation 3, we can substitute y from here into this equation, and we can further write this as y minus 1. We can further write this as less than equals to y minus 1 into mod y as and y can be written as 1 by y can be written as 2 by y, which is less than equal to 2 by 1, right? So less than equals to 2 by 1. If I write it in a better way, I will write it as 2 into y minus 1 upon mod of y squared. Now let's use our epsilon k definition, and let's say y minus 1 less than equals to epsilon by 2 into mod y squared. अभी मिटा दिया है
चलो कोई ना, ठीक है, सही।
इसका काम था
किसका? अबे काम नहीं था, चल
कोई ना let me call this equation 6. Equation 4. Now let me do equation by using equation 4 and 5. We can write 1 by y minus 1 by y is less than equals to epsilon. And once we get to this equation, we can by the epsilon k method, we can conclude that the sequence is 1 by y attributes to 1 by y. So now that we have told that our sequence 1 by y attributes to 1 by y, we have to just have to use our equation, our second theorem, and continue our proof further. So by using theorem 2, we can conclude as summation set upon y attributes to x5. Thank you.
सर, एक्स्ट्रा मार्क्स प्लीज़।